In this video, we will use our knowledge of the equilibrium expression to determine the pH of weak acid solutions. First of all, we have to remember that weak acids ionize to varying extents. Strong acids, remember, react or ionize 100%, whereas weak acids react less than 100%. The stronger the weak acid, so a stronger weak acid will ionize more than a weak acid. Put another way, they will react more for a stronger weak acid. Or another way to put it is that their K expression, their equilibrium expression value, will be greater than the K for weaker acids. So as we mentioned before, strong acids ionize 100%. That is, their K is infinite. If we set up an ice table for a initial concentration of 0.1 moles per liter, we find that all of it at the end, there will be no noticeable amount of hydrogen chloride, and all of it will be ionized into hydronium and chloride ions. So again, if we were to set up a equilibrium expression, it would be 0.10 squared divided by 0. And as you know from your math courses, dividing by 0 gives you an infinite number or undefined. So this K value is really big or undefined. If we're to look at a weak acid, however, so something like that would ionize 1.7%, such as acetic acid, we're looking at our ice table, we find that initially, even though we have 0.1 mole per liter acetic acid, that only 0.0017 moles per liter of hydronium is found at the equilibrium. So that at the equilibrium, the concentration of acetic acid is 0.1 minus 0.0017 moles per liter. And if we're to do an equilibrium expression for it, we find that the K for this reaction will be very small. Now chemists have determined the equilibrium expression for the forward reaction, that is, the reaction of the weak acid with water. In your acid-base table in your data booklet, you will find a column on the far right with a column of Ka values. You will notice that it is ranked in decreasing order. The strongest acid, the largest K, is at the top, whereas the smallest K is at the bottom. If we're to look at your table of acid and bases on page 8 and 9 of the Chem 30 data booklet, you'll see that the first 6 acids are very strong acids. In fact, they're so strong, again, that the Ka is just called very large, almost infinite. We say that these acids ionize 100% to form hydronium. Everything else in that data table is to be considered weak acids. While in earlier courses you're not asked to calculate the pH of weak acid solutions, in Chemistry 30 you will be. Let's look at an example now. Propanoic acid, here's a formula, is a weak monoprotic acid. A student prepared a 0.10 mole per liter solution and found that the pH was 2.96. And we're asked to find what is the acid ionization constant and what percentage of the molecules were ionized in the solution. So we're asked to find the Ka and then determine in terms of percent what percent of the original propanoic acid was ionized into hydronium and propanoate. All that we're given is that the original concentration of propanoic acid was 0.10 and the final pH value is 2.96. The first step we'll need to do is to determine the ionization equation, which we have here, and then set up an ice table underneath. Remember, in an ice table, we do not include the concentration of water because water is a pure liquid. So in this table, all the values are blank. I encourage you to just draw an X through that column so you do not have to worry about it. Next, we fill out our ice table using the information we're given. We're told that the initial concentration of propanoic acid was 0.10 moles per liter. And we know initially there was no amount of propanoate or hydronium. Now we can continue on with our change row. We know that a certain amount of propanoic acid will react, so that will be negative X. But for every mole of propanoic that ionizes, we're going to get 1 mole of propanoate, the conjugate base. Similarly, we're going to get 1 mole, or 1x, of the hydronium. So at equilibrium, we know that the concentration of propanoic acid is 0.10 minus X, and the concentration of propanoate is X, and hydronium is X. Before we move on to off the ice table, we were told that of the pH of the solution was 2.96. Now, using the formula 10 raised to the power of negative 2.96, we can determine the concentration of hydronium. And as you see on the next slide, we can substitute that value here, and because the concentration of propanoate is the same, and here. We can also determine, using math, the concentration of propanoic at the equilibrium. As promised, we can now determine the concentration of hydronium, and it is 1.1 times 10 to the minus 3 moles per liter. Also, this is the same as the concentration of the conjugate base, the propanoate. Now we can set up our equilibrium expression, and it's a concentration of propanoate multiplied by the concentration of hydronium divided by the concentration of propanoic acid. As we mentioned earlier, we can now substitute in the values for X here, and then solve for 0.10 minus X, that is here. We can put it into our equilibrium expression now, and we do our math, and we find that the equilibrium expression, or Ka, equals 1.2 times 10 to the minus 5. And the last step is now to calculate the percent ionization of the original reactant, of the propanoic acid. And we can do that by just calculating the fraction, the number of molecules that ionize. Now, we know that only 1.1 times 10 to the minus 3 moles per liter of the propanoate, the conjugate base, was formed. However, initially we had 0.10 moles per liter of the propanoic acid. So the fraction, the percentage of propanoic acid that converted into propanoate is just 1.1%. And that value is our percent ionization of propanoic acid. A similar example is for us to calculate the pH of an acid when we're given its concentration. So here, methanoic acid is present in this thing of certain ants. What is the pH of a 0.25 mole per liter solution of methanoic acid? So we're asked to find a pH, and we're given that the concentration of the weak acid is 0.25. We can also determine, by looking at our table of acids and bases, that the Ka for methanoic acid is 1.8 times 10 to the minus 4. So the first thing we need to do, step 1, is to set up our ionization equation. Luckily for us, everything works out into a 1 mole ratio. Next, we set up our ice table. Again, we do not include any amounts that deal with water because water is a pure liquid, and we do not include it in our equilibrium expression. We're told initially that we have a concentration of 0.25 moles per liter of methanoic acid. We know there's no methanoate, the conjugate base, and there's no hydronium. Some amount, let's call it X, of methanoic acid will ionize, so the change for methanoic acid is negative X. If the change for methanoic acid is negative X, then the change for methanoate, the conjugate base, will be positive X. Similarly, hydronium will increase by X. Lastly, we can use algebra to determine our equilibrium concentration for methanoic acid to be 0.25 plus negative X, or just minus X. And the equilibrium concentration of methanoate is just X, and same for hydronium. If we were to solve this in a straightforward manner, we would now set up our equilibrium expression. So the equilibrium expression, or Ka, is the concentration of methanoate, X, multiplied by the concentration of hydronium. so now x squared, divided by the concentration of methanoic acid leaving at the equilibrium, so 0.25 minus x. We now realize that even though we have a value of Ka, we do not have the value of x. We need to solve for the value of x. However, x here is being squared, whereas x here is not. This would suggest that we're dealing with a quadratic equation. If you are comfortable dealing with a quadratic equation, you are more than welcome to solve the equation as is. However, I will now show you a trick that we can cancel out this minus x so that we're dealing with just a straightforward squared equation. The trick I was referring to the last slide is to determine that the percent ionization is not significant compared to the initial concentration of the acid. In order to do that, we need to determine the value you get when you divide by the concentration of the acid, divided by the equilibrium constant, Ka. If this value is greater than 1,000, we can safely assume that the ionization is not significant. So therefore, instead of writing in 0.25 minus x as the equilibrium concentration of the acid, we can say x is nearly 0 or approximately 0, so that the concentration of the methanoic acid at equilibrium is just 0.25. We can now take the 0.25 value and substitute it into the equilibrium concentration of methanoic acid. And the concentration of methanoate and hydronium is still x, because even though it is small, it is still significant. Looking at our table of acid and bases, we can find that the Ka for methanoic acid is 1.8 times 10 to the minus 4, and this side of the equal sign is just the equilibrium expression, x times x divided by 0.25, as we saw in the last slide. We can now solve for x by multiplying both sides by 0.25. So now the left-hand side of the equation is 4.5 times 10 to the minus 5. The other side of the equation is still x squared. Next thing we do, we square root both sides, so that we find x is 6.71 times 10 to the minus 3. We can now go back to our ice table and we say that, oh, the equilibrium concentration of hydronium is 6.71 times 10 to the minus 3. The very last step is to find the pH of the solution. And again, the pH is merely the negative log of hydronium concentration. So in this case, the pH is the negative log of 6.71 times 10 to the minus 3, which rounds to 2.17. So then our final statement is that the pH of a solution of 0.25 mole per liter of methanoic acid is 2.17. Again, I remind you that after you determine the pH value, only the digits after the decimal are considered significant. So in the value of pH of 2.17, there is only 2 sig digs. And as a last point, no questions in Chemistry 30 will require you to use the quadratic formula. However, some questions may ask you whether or not the assumption that we can say the amount of ionization is small to be true. So then you would have to determine if the concentration of the acid divided by the Ka is greater than 1,000. You should always develop the habit of checking for this before you do any calculations. You should also make a statement in words saying that you have checked for this assumption and this assumption holds true for your particular question.